Hey metric students, in this lecture I just want to briefly outline classification tables and talk to you about how we'll be using those in the lab and how to think through the goodness of fit in the model and the diagnostics that you can get from that. Alright, so now let's talk about the basic classification table. I'm just going to be using the example from class. In another lecture I might introduce some other examples. But this is the classification that you should have gotten in lab using a cutoff of 0.5. So what we have here across our two different rows are the true values for the deny. Whether deny actually happened, that's just happens to be D, or whether that's 0, not D for your dummy variable, that's actually not always going to be deny, and this is how it was classified, so how you predicted. Positive, negative is how that is symbolized. Another way, this is the default way if you're doing a logit model, this is the table that it will spit out and the terminology that it uses and the symbols that it uses. We also could classify it this way, where we have D hats are predicted values for whether the individuals are denied alone or not, and are actual D1 and D0. So this is for a cutoff of 0.5. And what you might notice are there for a cutoff of 0.5, very few that are actually predicted to be denials. If we lower the cutoff to that 20% threshold, a predicted probability of 20% or more gets classified as a denial. The number that we predict will be denied obviously increases. Now what I do want you to notice is that these numbers, the actuals, are not changing. It's 273 and 1967. Changing your cutoff value obviously does not change the actual. So the totals in that column do not change. However, the totals across your rows, your total of your predicted, are changing. So you can't move across the actuals, you simply are moving observations from predicted denials, from predicted acceptances to predicted denials. What I really want to introduce in this lecture, though, are some very key terms, just two main ones. Sensitivity, which is the share of true ones that are correctly predicted, and specificity, the share of true zeros that are correctly predicted. The important thing I want you to note is that correctly predicting is a choice in terms of the fact that it depends non-trivially on that cutoff. The cutoff is determining how big the probability needs to be before you predict a value of 1 for your dependent variable. In our example, our dependent variable is denies, so how high does that probability of denial have to be for you to predict that value of 1 as the predicted value? It will be the case that 0.5 is going to maximize the total number of correct. However, this is not always going to be the thing that you want to maximize. So when you're doing any sort of model like this, you need to think carefully about what are you trying to maximize in the picking of a particular cutoff. It obviously depends on what you're modeling and what the sort of loss is for getting something wrong. Let's look again at this classification table and calculate these two statistics. So the sensitivity is the share of true ones, so our denominator is going to be 273 that are correctly predicted. So out of those 273, They should have all been 1s if we were predicting them all correctly. But instead, we only predicted one of them. So our sensitivity is 1 out of 273. So this is an abysmal 0.37%. Now let's talk about specificity. So this is the share of true zeros. So our denominator is going to be this 1,967. No matter what cutoff we do, or what we use to classify our model, with this data set, our denominators will be the same. For sensitivity, it will be 273. For specificity, it will be 1,967. Of those, we've classified almost all of them as denials, 1,966. So we had an incredibly high rate of specificity, 99.5%. The total correct is the sum of those that are correct, that correctly classified, divided by the full total number. So divided by this 2,240 is what we are as the denominator. So the total correct with a cutoff of 50% is almost 88%. Now let's look at this same exercise with a cutoff of 20%. So we're lowering the threshold to predict a denial. Again, sensitivity, that's the share of true ones that we're correctly predicting. Same denominator, very different numerator. Previously it was 1, and now it's 170. And now we are predicting 60, almost 62% of those correctly. Our specificity is the share of zeros. So true zeros, we had 1,967. However, instead of predicting 1,966, we've dropped. We're only now predicting, I'm sorry, this is a typo here, 1,698. And in terms of correctly classifying, what we have is 1,868, or 84. And this is a smaller percentage than we had with the 0.5. So if we were trying to maximize this correctly classified, we would go with that 0.5 cutoff. However, that is basically giving us no information about predicting those who are actually denied. I will talk a bit in a bonus lecture, an extra lecture, about Bayes' rule and how sensitivity and specificity play into that. But right now I just want to show you this visualization that Stata will make for you if you're running a Logit model of the cutoff, the trade-off that you face between sensitivity in blue and specificity in red. If you are setting your cutoff at 0, that is the best way to guarantee a very high sensitivity. So if our cutoff is 0, then we'll actually be assigning everything into denial equals 1. So the sensitivity is the share of true ones. If we're classifying everything as a 1, because our cutoff is 0, then we're getting 100% in sensitivity. If we go to the other extreme and classify nothing as a 1, then we are classifying all of our zeros correctly. So specificity goes to 1. This allows you to visualize the different cutoffs. So here is where we were with that 90, with that 0.5 cutoff, and then down here is what we were looking at with that 0.5 cutoff. It shows you in a very digestible format the particular trade-off that you're facing, and you can see where you're having the most movement, right in that middle section. It doesn't give you the answer to what that cutoff should be, but it does allow you to visualize well the options. Thank you again for watching. I hope you are all hanging in there doing well. We're getting close to the end here. Just about done with our penultimate chapter on binary variables. Hope to interact with you soon. Take care.